Hello, we will cover principal component analysis. So principal component analysis. Principal component analysis. Well, we have some explanations. Let's check the Wikipedia. So the principal component of a collection. So we can check it. You can skip this part. PCA is used in exploratory data analysis and for making predictive models. And it is commonly used for dimensionality reduction. Okay, so what is dimensionality reduction? It is a very important concept. Dimensionality reduction or dimension reduction is the transformation of data from high dimensional space into low dimensional space. So suppose we have like a three-dimensional data, we can project it to the like a two-dimensional data. Okay, like we have space and we take picture, then it becomes two-dimensional, right? Something like that. So dimensional reduction is the transform high dimensional space into low dimensional space so that the low dimensional representation retains some meaningful property of the original data, ideally close to its intrinsic dimension. Okay, so let's go back. So it is commonly used for PCA is commonly used for dimensional reduction by projecting each data point onto only the first few principal components. So projecting each data point into new, like a new axis. Here, principal component, you can regard them as axes to represent the data. And then those principal components are orthogonal to each other to obtain low dimensional data while preserving as much data variation as possible. So let me skip and then let me go to the, well, there are a lot of explanation. I think they are all good. So intuition, skip intuition and go to the detail. Okay. So PCA is principal component analysis defined as the orthogonal linear transformation. So it is linear transformation, and then we will learn non-linear transformation, such as autoencoder shortly. But PCA is orthogonal. So axis in PCA, so principal component analysis. So principal component in principal component analysis are orthogonal to each other. And then they transform data to new coordinate system. In the new coordinate system, they are orthogonal to each other, such that graded variance by some scalar projection of the data comes to lie on the first coordinate. Okay, so we represent the data into the new coordinate system, and in the new coordinate system, the first coordinate is exactly in line with the direction of largest variation. So I saw the figure over here. Yes, here. This is a good figure. So we have currently X and Y, right? We have X and Y here. We have this one, this x-axis and this y-axis, right? And then we want to express this data, they are the data point into new coordinate system. And then this is the new coordinate, new x and new y. And this new coordinate system is quite interesting because the first coordinate, which is this one is to the direction of the greatest variation of the data. To this direction, we can see the greatest variation of data. So that's why we set the first principal component or first axis, first coordinate over here in this direction, right? And once we remove this part, remove this direction of the data, then next coordinate should be this one. And they should be orthogonal to each other. So anyway, it is two-dimensional data. So this is maybe this is the only orthogonal direction over here. So principal component analysis, like this is original coordinate system, and we find new coordinate system such that the first principal component is to the direction of a maximum variation, and second coordination is orthogonal to the second coordination, and explain remaining variance of the remaining largest variation. Good. And then let's go back. So let's go to the detailed parts. New coordinate system such that greatest variance by some scalar projection of the data comes to lie on the first coordinate. That's what I explained. Okay, called the first principal component. Okay, so the first coordinate, which is, if we normalize it to the unit distance, unit length, it is called the first principal component. And the second greatest variance on the second coordinate, and so on. Now let's consider we have n multiplied by p data matrix x with column-wise zero empirical mean. So we normalize data such that the data is zero mean. The sample mean of each column has been shifted to zero, which is easy to do that, where each of the n rows represent a different repetition of experiment, and each of the p columns give the particular kind of features. So p is the features, and we want to reduce p. So mathematically, the transformation is defined by a set of size L of p-dimensional vector of the weight or coefficient. Here, WK, W1, WP, that maps each row of xi, x to new vector of principal component scores like this. So, okay, so what it does is that this is now very important, very important. Okay, so we have this original data. We have this is original data. So the row is n, okay, and this is k, okay. This is our original data, and then we want to do dimensional reduction. So we want to modify this one to such that fewer number of features. So we have the same length of the n, but now we have L. Okay, so K is greater than L. Okay, so we want to reduce the dimension of this original data. The dimension is K into L dimensional data as little loss of information as possible. Now, how to do that? Okay, we can do simple matrix algebra. We can do this one. Okay, we can do this one by multiplying some matrix over here. Okay, so what we can do is, okay, by multiplying over here, what we can do is, we have L over K. Okay, so here length is K. So we multiply these two matrices, then it becomes basically this one, right? This is the linear algebra, elementary linear algebra, Ln. Okay, so here, W, this is W. Okay, this is W. Okay, and then, yeah, something like this one. So, and then this here, this T is over here, T data. Okay, so in principal, our goal of principal, what we do in the principal component is to find this one. So we find each of this one. So each of this column is basically linear combination of these k vectors, right? So by finding this column, we first find linear combination k to generate the first principal component. And the second, in the second row, this second row is a second linear combination of these columns, which generate a second principal component, something like that. And they are all orthogonal to each other. Okay, that's what it does. So let me say again. So mathematically, the transformation is defined by a set of size of L of p-dimensional vectors way W of or coefficient WK. Okay, and this each has length of K. Okay, that maps each row of the xi of X to a new vector of principal component score, as I explained, given by this one. Okay, in such a way that the individual variables T1 to TL of the T considered over the dataset successfully inherits the maximum possible variance from X because the variation in X is the information. And since the first principal component extract most variance and second variance in such a way that by reducing dimension we can still keep the most variation, which means the most information. Okay, and a constant unit vector. Okay, where L is usually selected to be less than P to reduce dimensionality. Okay, so well, mathematically it becomes more straightforward. So look at that. So how to get the first component? Okay, so in order to maximize the variance, the first weight W1 has to satisfy this one. So here we want the first weight has the sum to one. That's what it does, sum to one. And then the first one is basically solution of minimizing, actually maximizing T1, actually variance of T1, which is the first one is basically xi multiplied by w, right? So again, we have this original data k, and then we find the first weight vector, this is 1, and the length is of course k, the length is k, and then we find the weight of this one, okay, which have like k number of elements in this vector, and that is of course linear combination of this k vector, such that the sum, the length of this vector w1, length is 1, like this one, and then we want to find the combination of k that maximizes the variation of the vector. Okay, so it generates t vector, which is 1, 9, 1, 9, and then we want to make this one as big as possible. Okay, we want to make the size of this one, basically variance of this as big as possible. Okay, as big as possible meaning this way, by this meaning. Okay, maximum variance. Okay, so in the matrix form, we have W1 is basically its length is 1, and W square distance is basically we want to maximize it, and then it has a representation of this one. Okay, since W1 has been defined to be unit vector, it is equivalent also satisfy this one because this term is equal to 1, right? The quantity to be maximized can be recognized as Rayleigh quotient. You can forget about it. A standard result for the positive semi-matrix such as X prime X is that quotient maximum value is the largest eigenvalue. Okay, this is important. Now in matrix algebra, basically, we have something called eigenvalue decomposition. So it means that finding the first principal component is basically equivalent to finding the largest eigenvalue in eigenvalue decomposition. Okay, and once we find the eigenvalue, the corresponding eigenvector is basically W, the solution. So again, this is very important point. Important point. Principal component is solving this problem, and equivalent way to solve this problem is to get the eigenvalue, largest eigenvalue of this matrix, largest eigenvalue of this matrix, and W is the eigenvector that is in line with this largest eigenvalue of this one. How about second principal component? Second principal component is exactly same. Second principal component is basically, second principal component is equivalent to finding second largest eigenvalue of this matrix, and the weight is the eigenvector that it corresponds to the second largest eigenvalue. Once we find the eigenvector, which is basically W, then by multiplying that n by k matrix with the second eigenvector, then you will get second principal component. And third principal component is again equivalent to finding third largest eigenvalue, and weight is third largest eigenvector, and by multiplying third largest eigenvector to the original matrix, you can get the third principal component. This is very important. Okay, let's go back to original mathematics. And then once we find, suppose we compute the first principal component with this maximization problem, then further component is like this. The case component, suppose we have k minus 1's component. So now the next case component can be found by subtract the k minus 1, the previous principal component from x, original data, x. Okay, basically from original data, we subtract the first k minus 1 principal component, and then we have a new matrix, and within the new matrix, we find weight matrix that is of course normalized, that maximize the variation of this one. Variation of the linear combination, column linear combination. Okay, so this is the case component. So we know how to find the first principal component. Given that one, we subtract first principal component, and then using this formula, we can get second principal component. And once we have a first and second principal component, then we subtract that from the data, and then we can get third principal component, etc., etc. Okay, so student can read this one. And the covariance, yes, basically, yeah, we do eigenvalue decomposition of the covariance matrix, and then dimensionality reduction. Yes, this is dimensionality reduction technique. And single value decomposition, you can skip this. Further consideration, well, you can skip this. Symbol on abbreviations. Property as a limitation of PCA. I think this is interesting part. So if you have time, please read this. PCA information theory. Okay. You can skip. Derivation of PCA using covariance method. You can skip because basically this is, so this is basically code code to find the principal component. Yeah. So yeah, basically we are doing eigenvalue. And then PCA and the qualitative variables give application. So application, quantitative finance, yes. PCA has large applications in finance. And one of the very popular machine learning technique in finance. In quantitative finance, principal component analysis can be directly, can be directly applied to risk management of the interest rate derivative portfolios. Okay, so well, there are a lot of interest rate, 1 year interest rate, 2 year interest rate, 3 year interest rate, 10-year interest rate, and we have a lot of interest rate in line with the maturity. What when actually there are too many interest rate, now what we can do is we can do principal component analysis on the interest rate data. By principal component analysis, we can find a component that moves, okay, that moves interest data altogether. And then we can simply focus on that principal component to manage risk of interest rate related portfolios. Again, since we have too many interest rate, too many dimension, so we have to reduce dimension. Okay, then we do PCA, reduce dimension of interest rate data, and then we can focus on the principal, select the principal component, and then we can focus on that for risk management. And then trading multiple swap instruments. Swap is, well, it is like derivative, which are usually function of 3 and 500 other market quotable swap instrument is thought to be reduced usually 3 or 4 principal component representing the passive interest on a macro basis. Again, swap instrument is like a derivative which has a lot of sub instrument. It is like a basket of financial products. We have simply too many dimensions. Then we apply principal component analysis and reduce dimension, and we can focus on that principal component analysis to manage the risk of the portfolio swap instrument here. So converting risk to be represented as those two factor loadings or multiplier provide assessment of understanding beyond that available to simply collective viewing risk to individual 3 or 500 bucket. Okay, suppose we have 500 like interest rate data. Well, there is simply too many. And then it is very hard to characterize like 500 basket. Then what we can do is we can find 3 or 4 principal component. And then what we can do is we can investigate how each one in this 500 portfolio is correlated with each principal component. And then we can characterize each asset in the 500 portfolio. That's the idea. PCA has been applied to equity portfolio. Well, we applied it to like interest rate. Samely, we can also apply to equity portfolio in the similar fashion, both to portfolio risk and risk return. One application is to reduce portfolio risk, where allocation strategies are applied to principal portfolio instead of the underlying stock. Okay, so suppose we have 500 stocks. Again, maybe, well, maybe you are too busy, so and then maybe you have limited resources, so then in that case it is hard to manage 500 assets. In that case, what you can do is, again, you can do principal component analysis. By doing principal component analysis, you can basically reduce 500 assets into 3 or 4 dimensions. And these 3 or 4 principal components are actually linear combination of these 500 stuff, right? So again, here data is like this. So we have T years of data, and we have 500 number of stocks. Then we do principal component analysis, and then we have T years of data, and we have maybe just 3. Okay, 3 number of principal components. And these 3 principal component analysis are actually linear combination of these 500 stock. Therefore, these 3, each principal component can be regarded as a portfolio. They are also portfolio. So which means that instead of managing 500 portfolio, you can focus on managing just 3 portfolio. Okay, instead of managing 500 assets, you can manage just 3 portfolio. That's far more convenient. A second is to enhance portfolio return using the principal component to select stock with upside potential. Well, you can use principal component analysis to select stocks. First, well, you can focus on those 3 principal components, their portfolio. Then you can maybe find a good portfolio out of these principal components that is maybe good. Another one is that, well, while you are reducing the dimension of these 500 data, 500 number of assets into just 3 principal components, there are maybe some loss of information. And that loss of information is basically actually outlier of the data. Okay, outlier. So you have some data that is not spanned with these 3 principal components. You can regard that as outlier. In finance, outliers are interesting because they are likely to be mispriced assets. Mispriced means underpriced or overpriced. If it is underpriced, you can buy. If it is overpriced, you can sell, right? Therefore, again, by doing principal component analysis and finding outlier, you can find asset that is not well explained by 3 principal components. Then you can regard that as an outlier, and then maybe you can simply focus on those assets to generate excess performance. And well, quantitative finance is full of illustrations about principal components. And then neuroscience, there is another one. Relation with other methods, correspondence analysis, yes, that is very relevant. Fact analysis very important in finance. Well, I can skip this one. K-means clustering. We already learned K-means clustering, right? So with K-means clustering, you select the variable and then you can use a principal component. It has been asserted that relaxed solution of K-means clustering specify the cluster indicator is given by the principal component. Okay, so principal component is very useful. Okay. And the PCA subspace spanned by principal component identical to cluster centroid subspace, which means that instead of doing clustering analysis in the original space, you can reduce dimension and do clustering analysis at the reduced dimension. Then maybe you can have a clear result. And then generalizations, sparse PCS, nonlinear PCA. Nonlinear PCA is like rising area in machine learning. Very interesting, very exciting topic. And a similar technique, network component analysis, and then we have many software here. And then we will do some practice with Python shortly. Let me see whether we have a Python over here. Python, yes, Matplotlib Python library PCA package, the Matlab, yeah, module, good.